one of the problems in RF engineering is that you have, for example, a feeding signal generator, and normally the feeding signal generator has an internal resistance of 50 ohm, but sometimes you want to split the power, and one possibility is to do it like this. We would have here a transmission line of 50 ohm, so this is our transmission line of 50 ohm. I just write here the characteristic impedance 50 ohm, but I will assume that the length is almost negligible, so it's a very short transmission line. And to split the power, we now use two further transmission lines, which looks almost like this. And these two transmission lines I assume to have a characteristic impedance of 100 ohm. So what we have here is in principle a 3-port. So for example, this is port 1, this is port 2, or this is port 3. So this is a 3-port now, where the length of the transmission line I will neglect in principle. And now is also how does the complete S matrix of these 3-port looks like. So, and to start it, it's the easiest again to calculate S11. And as you remember, S11 is the reflection coefficient I see into port 1 here, under the condition that port 2 and port 3 are matched. So, and again, these two ports must be matched. And again, my question to you, what do I have to do now on port 2 and port 3? Can somebody answer?
Match 100 ohm load.
Yeah, we must connect here 100 ohm load here. So this is 100 ohm. We must terminate in its characteristic impedance 100 ohm. But again, if I terminate a characteristic impedance, a transmission line with 100 ohm characteristic impedance, then this has 100 ohm. This 100 ohm is transferred into this plane. So the equivalent circuit would be
Sorry.
one, yeah. Yeah.
Sorry. I think you the drawing is not correct, right? I mean you missed the port on
Which port?
for port 2 and port 3 the 100 ohms.
Yeah, here is port 3. This is port 3 here. Perhaps I write the 3 here. This is port 3. This is port 2. In both ports we have 100 ohm now.
So can we consider each wire of different branch like that, right? Oh, okay.
So this is one transmission line, 100 ohm, and this is the other transmission line.
Okay. I'm sorry. Okay. Yeah.
And you see now this 100 ohm is transferred into this plane with 100 ohm. What do we have now? We have here a transmission line with 50 ohm. And now we have two resistors here in this plane. So this now is this plane here. And here you have a 50 ohm. Sorry, not a 50 ohm, 100 ohm. And you have a further 100 ohm here. So what will be the load impedance here? I write ZL here. Of course, here it's our 50 ohm transmission line and it's terminated into these two resistors. And what about the resistor? What kind of connection do we have here?
Parallel.
So this is a parallel connection of two 100 ohm resistor. What is the value then for the load impedance?
50.
The value of the load impedance is 50 ohm. And what is then the load reflection coefficient if I terminate a 50 ohm transmission line with a load of 50 ohm?
One.
Then I write the equation again. It's a load impedance minus
0.
ZC over the load impedance plus ZC. And of course this is 0.
Yes, 0.
Yeah, we have a load impedance of 50 ohm, a load impedance which is also 50 ohm, so S11 is 0 in our case. Does everybody agree with this? Or are there further questions? So I can write now, I will write here S11, S11, according to our equation, it's 0. Or according to our considerations, it's 0. So now I delete again here. So in the next step, again, it's the easiest way now, for example, to think of perhaps we start with S22. S22, again, we can say this is equal to the load reflection I see into port 2 here. If, and the condition is now port 1 and port 3 must be matched. So, and again, what do we have to do to match port 3 and port 1? What do we have to connect to port 1, for example? An idea?
50 ohm.
So we must add here a 50 ohm. And what do we have to connect to port 3? Yeah.
100 ohm.
100 ohm. I always only hear one voice. Perhaps also the other students could sometimes tell me something. So you see here, now we have 100 ohm here, a 50 ohm here, and again we see, I want to sketch it now like this. I have here a transmission line of 100 ohm, and again we have now two resistances in parallel in this plane here. And this means we have here a 50 ohm and here, perhaps I sketch it a little in a three-dimensional manner. So you would see here the 50 ohm, 50 ohm, and here again we have here 100 ohm. So we will have a load resistance now, or I call it load impedance. The overload load impedance now will be equal to the parallel connection of a 50 ohm parallel 100 ohm. I just write like this: 50 ohm parallel 100 ohm. And if you calculate the value, then it's 3.33 ohm. This will be the parallel connection. Of course, you know, the parallel connection is always smaller than the smallest resistance here. So we will have a 30.3 ohm. And we can now calculate again RL in our case. I use the green color. In this case, RL is equal, you see here, 33.3 ohm minus 100 ohm divided by 33.3 ohm plus 100 ohm. And if you calculate the value, then you will get this is minus 1/2. So we see now that as 22, it's equal to load resistance here, load reflection coefficient, and it's equal to minus 1/2. So we can conclude here as 22 is minus 1/2. Are there some questions considering now the derivation here? So there seem to be again no questions. Then we again consider the symmetry. You see here, if I interchange port 2 and port 3, for example, if I would name this to be port 2 and this to be port 3, we would get the same considerations here, or end up in the same considerations. So we can conclude that S22 is equal to S33. So these both are the equivalent. So we have S11 is 0, S22 minus 1/2, and this is equal to So are there some questions? Now, considering all these considerations or the thoughts we did. So now if there are no questions, then I now delete here and set up the new or include our results into the scattering matrix. So what do we know now? We have here 0. I call this S21, S31. Oh. We have here S12, S32. Here we have 1/2, S23, S32. Here we have also -1/2. So this is now our scattering matrix. We already know these elements of the main diagonal. Of course, since we have a passive component, we have its reciprocal, it's written of course with a C here. Reciprocal, perhaps I call it reciprocal, it's reciprocal. This again means that these elements are the same. So we can say we have here 0, S21, S31, and here we have in principle also S21 -1/2, and we have here S31 also. This must be 1 here, sorry. And here we have I can say 2, 3, then we also have here S2, 3, and here we have 1/2. So, and of course, now we can also account for the symmetry. If we account for the symmetry between port 2 and port 3, which means we cannot interchange or cannot distinguish between port 2 and port 3, we must also have here the element S21. So the wave enters into the 50 ohm transmission line, it cannot distinguish between port 1 and port 3. So the transmission factor from port 1 to port 2 must be the same as from port 1 to port 3, and so we can use here this, and we can also say that this must be 2 here, equal to 2. So, and now we can set up the absolute value condition. The absolute value condition, and of course then we have in principle to take the absolute value of this plus the absolute value of this plus the absolute value of this. This must be 1. And from this you see that we have that 2 times S21 absolute value square must be 1, and from this we find that the absolute value of S12 must be equal to 1 over the square root of 2. So we end up now in 0, 1 over the square root of 2, 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 minus 1 half, and here we have S23, S23 minus 1 half, and also since again this is a lossless two-port, we can now say this absolute value plus this absolute value square plus the absolute value square of this must be 1 again, and we can conclude now I delete this here. We can conclude that the absolute value square of 1 half is 1 half here minus 1 over 4 plus the absolute value square of S23 must be equal to 1, and sorry, here of course it must be here 1, and then you see that the absolute value of S23 must be equal to the square root of 1 over 4, and this will be 1 half again. So at the end we now get the whole two-port. Perhaps I sketch here. So the overall S matrix of this lossless power divider will be 1 over the square root of 2, 1 over the square root of 2, 1 over the square root of 2, minus 1 half, 1 over the square root, no, here not. Here it must be 1 half, and here we will have 1 over the square root of 2, 1 half, minus 1 half. And of course you again can prove this by applying now the phase conditions, and if you would apply the phase condition to this 3 by 3 matrix, then you would see also the phase condition is fulfilled, and we can say due to the fact that we neglect the length of the transmission line, there will be no additional phase shift in this power divider. So did this become clear, or are there questions here?
Sorry, so for the reciprocal condition,
Yeah.
I mean, so is the lossless and quark system like a passive network, so that the scattering matrix become reciprocal?
Yeah, always if we have a passive network, which means we have only some inductances in it, resistor, capacitor, it becomes reciprocal. Of course, as soon as a resistor is in the network, then it shows some losses. But nevertheless, as long as it's passive, it will be reciprocal. So, yeah. Did this answer the question again?
Yes, and we don't prove the phase condition here because we consider the transmission line the length to be negligible.
Now you can prove the phase condition. So you must in principle take this times the complex of this, and this must be 0, and then you will see that the phase condition is fulfilled. And the argument is I did not introduce any phases because the transmission lines are very short. So this is why there is no, you don't have to account for the phase here. But if you would now check the phase condition would be fulfilled in this network.